Hi folks, this is Dr. Rob Cywes, and I've had a lot of discussion with my patients who follow other people, and they do their NMRs, the nuclear magnetic resonance, and they want to know all about the ApoBs and the ApoAs and all the fractions of, and they're spending shit tons of money, awful amounts of money. I've got to stop using that. No, I like using that word. I'm not going to stop. If it offends you, leave a comment. But I'm going to have a discussion about the biology of lipids in the human body. And I'll dumb it down slightly, but it's very accurate the way we talk, at least to the knowledge that we have right now. So all of our lipid molecules, all of the transport molecules, the transport lipids, originate and are made by the liver. The liver is the original site of all of the lipid transport molecules that we have. And they've all got different names, and we're going to go through how they form and what they're made of. So the first thing that why do they exist? Because the human body, for the most part, is aqueous, which means it's water loving. The problem with fat is fat and water, as you know, are polar opposite. So what we have to have is a vehicle to transport fat and fat type of substances in an aqueous medium. So if ever you've looked at droplets of fat in water, you'll see the droplet of fat sits there and floats in the water. That's how we transport fat in our body, but we have to create that droplet, and it's got a little membrane around it. And the membrane is formed by two things. It's formed by a little lipid biolayer, a cholesterol and lipid biolayer, and inside of it can be fat-soluble vitamins, triglycerides and fat, and cholesterol. And also phospholipids, which are used to build cell membranes. So all the different types of fat are carried and transported in this. Yes, we could transport fat free in the bloodstream attached to carrier molecules like albumin and globulin. Those are called non-esterified fatty acids. But for the most part, fat is transported around the body in these vehicles. Think of them as Amazon delivery vehicles bringing your parcels to your house. Now, the membranes are hydrophilic on the outside. They like water on the outside, but on the inside, they like fat. They're lipophilic. So it's this polarized membrane that is water loving on the outside, fat loving on the inside because of the way they transport things. The second thing is these membranes all have different proteins in them called lipoproteins. So you've got ApoB, ApoB100, or ApoA. You've got different nomenclatures for the ApoB, ApoA molecules, which are proteins. But if you think about the proteins, they're basically zip codes. So what these proteins have, they hang out in the membrane, and there are receptors for these proteins on various cells. And when they dock to the receptor, that's how they know where they're going. Just like the Amazon driver has a zip code and address, and the zip code takes them to your house to deliver the package, that's exactly how these molecules work. And the apoproteins are basically the zip codes that take them to fat cells, take them to macrophages, take them to dock with other lipoproteins, take them to different vehicles or different sites where they dump their loads. The liver makes cholesterol and makes these vehicles. The first one we're going to talk about, which is the least important, very important to your body, but the one that's got the least focus, is the liver forms bile salts and bile acids. The bile travels through a particular little vessel called the bile canalicula. It goes down the bile duct to the gut, and some of it is stored in the gallbladder, so that when you eat, especially a fatty meal, the gallbladder contracts and releases it. But it's irrelevant whether you have a gallbladder or not. It's irrelevant. Oh, you don't have a gallbladder, you're not going to be able to absorb fat. Bullshit. Ignore the fact that you do or do not have a gallbladder. It is irrelevant, and you don't have to take any of these. Oh, your bile is forming stone. Bullshit. Your bile is running down. Unless you're bright yellow, you are releasing bile into your gut. And if your poop is brown or any form of brown or green, you've got bile in your brown. Don't ignore that. So the bile that gets deposited by the liver has a couple of functions. First of all, it's a waste product for extra cholesterol. It's a waste product, and that gets pooped out. Secondly, however, the bile forms a little soap bubble. And the soap bubble in the gut can trap fat, cholesterol, and fat-soluble vitamins like your vitamins A, D, E, K, the various ones of those that get placed in these bile bubbles so that they can then be absorbed into your cells. And there's certain parts in the intestine where you form a transport molecule out of that bile micelle, and it's called a chylomicron. And it's the biggest of the transport molecules that fill with a fat in your diet. And the chylomicrons get absorbed across the intestinal lining, and they are the only things that do not get transported to the liver via the bloodstream. The chylomicrons are these big molecules that get taken up in the lymphatic system. And the lymphatic system collects all of this fat from the gut. And after a meal, if you look at the lymphatic system in the gut, as I do as a surgeon, it's pure white. It looks like milk. Okay? And it travels up the chyle, which is this milky substance full of chylomicrons, travels up the thoracic duct and dumps into the left subclavian vein up in the left neck, and then goes into the bloodstream. But before we go ahead, folks, sometimes we drop out of the optimal range of ketosis, which is about 0.5 to 2. And the best way to get in there is to eat fat, but sometimes we need that little burst. And Cheryl and I have done a lot of experimentation. Ketone IQ is the best product we found to rapidly restore optimal ketosis. Whether you're going to exercise, whether you're working, whether you need to be awake, popping one of these babies in tastes a little bit crappy, but gets you into the optimal range very quickly and keeps you there for 3 to 4 hours. Look at the show notes and you will see a promo code that'll get you 20% off. So it gets taken up by the lymphatics and goes into the systemic bloodstream and then gets distributed directly to your fat cells. So the primary site of chylomicron deposition and the proteins on the chylomicrons take this to the fat cells where they dump their load, and you store those in the fat cells. So you're storing cholesterol, you're storing fat, you're storing triglycerides, you're storing long-chain fatty acids, and you're storing fat-soluble vitamins in your fat cells, including things like 3-omega fatty acids. So they get transported in chylomicrons, go to your fat cells. And one of the big issues with certain food products, especially plant products and fiber and that kind of bullshit, fiber is food. No, it's not. Food for a cow, not for humans. But they absorb these biomicelles and you poop them out, which means that you are running at a cholesterol and also a fat-soluble vitamin deficit. A lot of people that believe cholesterol is bad for you, oh, you must eat these plant products, you must eat them to poop out the cholesterol. Oh, you've got to eat your cereals to poop out cholesterol. That is not a good thing. Because you're also pooping out fat, you're also pooping out your fat-soluble vitamins. So a bad thing, not a good thing. Nevertheless, there's this enterohepatic liver to gut recirculation of these chylomicrons. And once these chylomicrons have dumped their load at your fat cells, they then are small little units called chylomicron remnants. They come back to the liver and the liver reprocesses them. So the liver takes those boys up and reprocesses them. And in part, the apoprotein nature has changed. So the first address was your fat cell address, and then the fat cells changes the apoproteins and sends them to the liver, where they now have a liver address, and they get taken up by the liver and either destroyed, broken down, or repurposed, reprocessed. So that's the chylomicron circulation. The liver then will take extra sugar, whether you've eaten carbohydrates or extra protein, and the liver then takes extra sugar and extra protein, turns the protein to sugar, stores some of the sugar as glycogen, but there's a very finite capacity of around 400 to 600 grams in the liver, and then those stores are full. And then the excess sugar is converted by the liver to fat. And the fat that we produce in the liver cells is packaged together with a molecule called glycerol. So you've got 3 fatty acids and a bar of glycerol, and they are called triglycerides. So when your doctor measures triglycerides in your bloodstream, in your blood test, that is pretty much the triglycerides that are formed by the liver when it's converting excess sugar or excess protein via sugar into fat. That's what triglycerides are. So triglycerides are a direct measure, a marker of your blood sugar. And the higher your triglycerides are, the higher your blood sugar is, the more risk there is to your cardiovascular system, except when you're obesogenic, where the liver is clearing it so well that you've got this big fatty liver, but your blood sugars are normal. But they are a direct marker of sugar issues in your bloodstream. And the fat cells sit in your liver, and that's what we call a fatty liver. So non-alcoholic fatty liver disease is caused by the conversion of sugar to fat, and the fat is trapped in the liver because the liver is very quick at making it, but very slow at transporting it out of the liver. But the liver then also forms a lipoprotein molecule called VLDL, very low density lipoprotein. It's a big molecule, a small molecule, and VLDL can either be small and dense or large and fluffy. If you are putting the triglycerides into the VLDL, two things happen. The size of the VLDL gets big, and the VLDL is going to transport cholesterol, triglycerides, and also phospholipids that are made in the liver. What are phospholipids? They are used in cell membranes. So the liver packages all that extra fat into these VLDL molecules. And if you've got big VLDL and a high number, it means that the liver is a primary producer of energy that it then distributes to the fat cells. So traffic is liver to fat cells. That is not a good thing. That is not a good thing. So a high VLDL number and a big fluffy VLDL, bad, not good. It means that you're over-consuming carbohydrates, and your liver is desperately trying to protect you from the damage of that extra sugar. Or you're over-consuming protein. So all those people that are pushing the protein narrative, they've got to look at your VLDL and say, good or bad, okay? However, the VLDL also contains certain apoproteins, which are your docking for fat cells. So the small, dense VLDL is the healthy one because it's going out to pick up fat from your fat cells, whereas the big fluffy VLDL is delivering fat to your fat cells. And you want the liver to be a recipient of fat, not a delivery system for fat. However, the VLDL number is important. And the ideal number for me with VLDL, if you're fat adapted and in ketosis, is a VLDL around 10 or lower. So when you're looking at your lipid numbers, one of the two, I think it's Quest or LabCorp, one of them do report the VLDL numbers, and you want that number around 10. And if your number is around 10, I can guarantee your triglycerides are going to be low. So those two always go together, because if your triglycerides are high, your VLDL is going to be high because it's the transport molecule. So here's the cool part. VLDL then leaves the liver, and it travels in the bloodstream, and it travels to your fat cells. The zip code is your fat cells. And when it gets to your fat cells, it does one of two things. It either dumps its load, so this big fluffy fat-filled VLDL dumps cholesterol, dumps triglycerides in your fat cells to store the fat, because that's what fat cells do. In part, Ben Bickman will corroborate this, it stores fat. And they form these fat dropules, but it combines with the membrane of the fat cell and dumps that load into the fat cells. When it does that, the big fluffy ones shrink down. But the small little VLDLs, the empty ones, dock to the fat cell, and guess what they do? The fat cell then dumps, and this is all regulated by insulin. So if your insulin levels are high, you're delivering fat to your fat cells. When your insulin levels are low and your glucagon levels are high, your fat cells are actually picking up. So under the influence of glucagon, your fat is now mobilizing fat, breaking fat down in the fat cells and dumping it into the VLDL. So your VLDL is getting fatter and bigger under the influence of glucagon, but under the influence of insulin, the big fat VLDLs are dumping fat in the fat cells, and insulin prevents the fat cell from breaking down and pushing fat out of the fat cell into the bloodstream, but also into the VLDL molecule. So insulin and glucagon not only regulates blood sugar, but it also regulates lipid traffic. Does that blow your brain a little bit? Okay, insulin regulates that. That's why insulin is more important than your lipids, because insulin regulates that at the fat cell level. Now, here's the cool part. Let's assume you're very healthy, you're fat adapted, that small VLDL number, that small VLDL molecule docks to the fat cell dumps a whole bunch of triglycerides, cholesterol, fat-soluble vitamins, all the good stuff into that VLDL. VLDL swells up. But here's what happens. It also changes its apoprotein. The protein, the zip code guy, changes. So when the VLDL now undocks, it's not called VLDL anymore. It's not VLDL. It's changed its name. It's called IDL, intermediate lipoprotein, IDL. And IDL can live in the bloodstream. It floats around the bloodstream for around 4 to 6 hours, very short-lived. And then IDL sheds some of its fat, changes its apoprotein. Guess what it's called now? LDL. LDL, low-density lipoprotein. So LDL, low-density lipoprotein, is not a unique molecule. It is a breakdown product of VLDL to IDL to LDL. And LDL can therefore have two forms. Either your LDL is big and fat and fluffy and filled with fat and cholesterol because it was the small VLDL that picked fat up from the fat cells, which is exactly what we want. That's the healthy, awesome pattern, the pattern A. If the LDL is small and dense because the VLDL docked with the fat cell, dumped its load from the liver, and now it's a shriveled up little molecule that's going back to the liver to pick up more fat, that small dense LDL is the B pattern LDL. It is a form of illness. It is a form of hyperglycemia because your liver is now sending fat to the fat cells. But if your fat cells are delivering fat to your body and you're fat adapted and in ketosis like I am as measured by this, my LDLs are big and fluffy and the number may be very high, but the volume is also high. And that is healthy, no matter what your doctor that wants you to put you on a statin is going to do. So the size and the shape of the LDL molecule is determined by the direction of the fat traffic, but it is a VLDL remnant. And then the LDL goes to your fat cells because it's a transport molecule, leaves the fat cells, goes to the other cells of your body that can use ketones, can use fat, can use non-esterified fatty acids, from your heart to your muscles to all the other cells to your brain, and delivers fat-soluble vitamins, triglycerides, and cholesterol for cellular utilization, cellular structure, and use as an energy molecule. And it brings it back to the liver, and the LDL remnant gets taken up by the liver. It reprocesses it, it uses some of the fat under the influence of glucagon to turn into ketones. So again, you've got fat being released under glucagon, so you're in fat-adapted ketosis, and your body is producing ketones, which are free-floating because ketones are short. They are hydrophilic. They like water. They can float around in the bloodstream attached to albumin and globulin. That's how some of the fat goes through the non-esterified fatty acids. And then the liver either breaks the LDL down or repurposes it to new VLDL. That's lipid traffic, folks. And I bet you most of your general practitioners that are putting you on statins do not understand that. And if your cholesterol is, your cholesterol is causing heart, no, it's not causing heart disease. If you have inflammation of your blood vessels and you form a clot, and the clot is cellularized, now you've got macrophages in your clot because there's damage to your blood vessels. The macrophages have an ApoB molecule receptor. So the LDL that's transporting fat to your body to use as energy docks with it, and it dumps a load of fat as spackle to heal up that injury. It's there to coat the injury. That's why your cholesterol is never ever a problem if there's no inflammation. If your blood sugar is high, you've got the inflammation. If your blood sugar is high, you've got small little dense LDL particles that are more likely to stick and dump cholesterol, which is dominant in the small dense particles, at the site of injury to your blood vessels. If you've got big fluffy LDL, it's done under the influence of glucagon, not insulin. You don't have high blood sugar, and you don't have the injury, so guess what? The traffic is just flowing nicely by. So that's LDL trafficking. And if your doctor doesn't understand that and can't narrate that to you and can't tell you about that, but he's prescribing a statin, that's a problem for me. Because they're looking at the numbers. And then we've got to look at ApoB particles, and we've got to look at esterification. Those are all just magical, mystical ways of thinking about lipids so that they can convince you that you should be on a statin. There is no reason for you to be on a statin. There's a lot of reason for you to be on medications or on a diet, ideally, that corrects insulin resistance, that lowers your insulin, that elevates your glucagon, that allows your lipid traffic to be healthy. There's no drug that can do that for you. There are drugs that can do it with you. And the value of the Ozempics and the GLP-1s is that's what they do. That's why the GLP-1s are more important than cardiovascular disease, as the SELECT trial has taught us. SELECT trial is a GLP-1 trial being done by Novo Nordisk, is much healthier for us than a statin. But this is the science behind it. And if you've watched this video and you know this and you can follow what I'm saying, you have more knowledge than most of your doctors. Know your lipids, but all you need, total cholesterol should be high, triglycerides should be low, total cholesterol between 2 and 500, triglycerides below 75. We haven't talked about HDL, I'm going to talk about that in a second. VLDL at 10 or lower, and we don't measure chylomicrons. You can in a laboratory, but we don't measure those. But your VLDL, your triglycerides, and your LDL, your LDL cholesterol should be 120 to 300, big fluffy molecules. Now, what's HDL? High density lipoprotein is a molecule that is produced by the liver during fat utilization under the influence of glucagon. HDL is your so-called good cholesterol. So what does HDL do? HDL goes out into the bloodstream, docks with your IDL and your LDL. It's got the zip code of LDL, docks with it and exchanges triglycerides and cholesterol and fat-soluble vitamins with LDL and changes apoproteins. So it is if you think about airplanes, you think about the Navy or the Air Force, where they have these big fueling planes, these planes that carry fuel, and they've got a little nozzle, and the jet comes up and sticks the nozzle in a little hole and refuels in midair so it can do these long flights. Beautiful. Watch it on TikTok. I sometimes do. That's exactly what happens with HDL. So HDL docks with LDL and IDL and exchanges the cholesterols, and then HDL breaks off and comes back to the liver and dumps the extra cholesterol and all the other waste products in the liver so it can get rid of it, while the LDL goes on and delivers energy to your cells and good molecules to the cells. So it's that mid-air docking system. And if your HDL is low, you don't have that exchange. HDL gets produced under the influence of glucagon by the liver. And if your insulin is high, your HDL level is going to be low. And if your liver is producing a lot of fat and you're defending your body against excess sugar, whether it be from excess protein or sugar, your HDL levels are going to be low. So HDL defines fat-adapted utilization, and it's this last number to really come up. So let's review again. Triglycerides below 75. HDL ideally above 75. These are American units. LDL 120 to 300. Total cholesterol 300 to 500. And VLDL around 10. That is the ideal lipid morphology, because it's going to tell me that you are insulin sensitive, and glucagon and insulin are working together because they regulate the lipid system. And what regulates and dysregulates glucagon and insulin? Sugar. Not fat, sugar in your diet. See how this all ties in, folks? Does that blow your mind? It's so simple. It's easy to be a doctor. I am the Carb Addiction Doc. If you like this narrative, if you like what we've done, throw me a buck on my PayPal account, okay? I'm doing this for free. I like this content. If you want to consult, if you want to know what your lipids are, should you be on a statin, should you not? Let's look at your CAC score. Let's look at your lipid numbers. Set up a visit, text, WhatsApp, call 561-517-0642. We'll get back to you. There is a waiting list. We can see you. I am the Carb Addiction Doc. I hope this has made you think. I hope this has made you understand or helped you to understand human biology. And even if you're a doctor or a healthcare worker out there, I hope this has given you a better, more scientific method of managing your patients' lipid profiles and glucose and insulin profiles. And if you don't know what the insulin and the glucagon numbers are, you shouldn't be prescribing statins.